I'm Anil Kumar, and in this video we'll find how to write non-equivalent polynomials when we are given two similar points. The question here is, determine two non-equivalent polynomials f of x and g of x such that f of minus 1 equals to g of minus 1 and f of 2 is equal to g of 2. So I'll show you two different examples with the help of which we could do similar questions, right? So when we say we have two common points, then necessarily the two functions may not be exactly same or equivalent. For example, I could have a graph of parabola like this and a line intersecting it, kind of like this. As you can clearly see, these two are not overlapping graphs. The only points which are common are 2, and that doesn't make them equivalent. For an equivalent polynomial, all the points should match, right? Now, we'll extend solving for the given condition. We are given f of minus 1 equals to g of minus 1. Let's call this function as f of x and the other function as g of x. Now, since it is a parabola, let me take a very simple function, the parent function f of x equals to x squared. Why complicate, right? Any two non-equivalent polynomials is what we are interested in. So if I say f of x equals to x squared, then what is f of minus 1 equal to? Will be 1, right? Minus 1 squared, which is 1. And what is f of 2 equals to? F of 2 is equals to 2 squared, which is 4, right? So we have the coordinates of these 2 points. Now you get it. How to get the equation of a line when the coordinates of 2 points are known to us? Simple. We want to find g of x. So let's write down what g of x could be. G of x could be mx plus b in general, a straight line. Now using these 2 points, we can always find m and b. So the slope m is equal to y2 minus y1, right? So we can say it is f of 2 minus f of minus 1 divided by 2 minus 1, correct? So f of 2 is 4, so we get 4 minus 1 divided by 2 plus 1, which is 3 over 3, or just 1. So the slope is 1. So we know when slope is 1, then we could write this as g of x equals to x plus b. To find b, we can use any one of these points. Let's use 2 and 4. So 4 equals to 2 plus b, or 4 minus 2 equals to b. So b is equals to 2, and therefore g of x can be written as equal to x plus 2. So the equation of the line becomes x plus 2. On the other hand, the function f of x, which we originally took as x squared, is the other function. And you can check that for these 2 points, their values are same. However, for other points, they have different values. Well, for non-equivalent polynomials, even if their value is different for a single point, they are not equivalent, right? That's the whole criteria. Okay, now we had to do a lot of calculations to get to the result. Here is a shortcut for you. Here is indeed a very, very good method. A shortcut which you'll all appreciate. Well, again, take the same example of parabola. Just to make things simple, let's say that's the example. And what we want is that the two values should be exactly same at f of minus 1 and 2. Let's think like this. It doesn't look like, but we can call this point x equals to minus 1, this point at 2. So if you consider a parabola with two x-intercepts, one at minus 1, the other one at 2, then what you get here is that f of minus 1 is equal to 0 and f of 2 is equal to 0. Now to get any other function which is not equivalent, we could think about other parabolas, right? With the same x-intercepts. For example, like this. Do you see that? Now they are not same, right? Well, if I change the vertical stretch, I could draw a parabola through this, kind of like this, right? So it's basically a family of parabolas which have same common point, which happens to be x-intercept here, but different all other points, right? So that could be a very easy example to give without doing any calculation. That's very important to understand. So I could write here f of x as equal to, since we have these two roots, we could say x plus 1 times x minus 2. And how about g of x? Same points, we can say g of x equals to, let's say minus 2 times x plus 1 times x minus 2. Does it work for you? Perfect, right? So we have met the condition given to us. These two parabolas represented by quadratic equations in factored form have two common points, but they are not equivalent. I'm Anil Kumar, and I hope this example gives you a key to answer similar questions for any polynomial. You can always put your likes if you appreciate it, but feel free to post questions, share my videos with your friends, and subscribe. Thank you, and all the best.